Okay. So today I want to set up the expression for the scattering amplitude for scattering off a spherically symmetric potential, and then compute the cross section, and then prove the optical theorem, and then I want to go back to the first Born approximation for the special case of a Yukawa potential, and the limit of the Yukawa potential, which is the Coulomb potential, as the mass of the Yukawa particle goes to 0. So let me get back to where we basically, I'll review some of the last things that we did. Just to get some formulas on the board. Something we're calling the free partial wave of momentum, well, wave number, let's say K, Lm of R, is the square root of 2k squared over pi. The spherical Bessel function JL of KR, and then the YLM of theta and B. And remember, the JLs are pretty simple functions, namely JL rho is minus 1 to the L, rho to the L, 1 over rho, dV rho to the L of sine rho over rho. So these are relatively simple expressions. And remember, in this partial wave analysis, it's very often the first partial wave, L equals 0, that's dominant, or maybe the second partial wave. So what we're dealing with here are pretty simple functions. The behavior of JL of rho as rho goes to 0 is something like rho to the L over 2L plus 1 double factorial. On the other hand, JL of rho as rho goes to infinity is minus square root of 2k squared over pi. Well, let me write something simpler than that. And in fact, let me use the top part of the board. In other words, JL of rho as rho goes to infinity is approximately 1 over rho sine of rho minus L pi over 2. And so if we examine, we're going to be interested, of course, in using phi 0 at large distances, and so we can say that that this goes to, as rho goes to infinity, this goes to minus square root of 2k squared pi YLM of theta and B, and then e to the minus I KR plus IL pi over 2 minus e to the I KR minus IL pi over 2, and all of that divided by 2I KR. Remember, in all this rho is equal to KR. And the reason why we wrote it in this funny form is that we want to identify, this is an incoming wave, we're going to relate this to the incoming plane wave, and this is the outgoing scattered wave. Any questions? Remember, I have chocolate. There's a famous expansion for e to the I kz, and it's equal to the sum L equals 0 to infinity I to the L square root of 4 pi 2L plus 1, and then JL KR, YL0 of theta. And YL0 of theta is the square root of 2L plus 1 over 4 pi PL of cosine theta. The reason why there's no phi dependence is that this just depends on z, so it doesn't depend on x and y, which would involve phi. It depends on x and y well, no, it doesn't depend on x and y at all. And so in terms of, in other words, z is r cosine theta. Okay, well, so much for the three, well, when we substitute for the YL0, we get a somewhat simpler expression. L equals 0 to infinity, pi to the L, 2L plus 1 because the square root of 4 pi's cancel, JL to KR, and then PL of cosine theta. Okay, so that's probably the nicest expression for the plane wave. Of course, we've tinkered with the normalization to make things simple, keep out a lot of extra factors of 2 pi. Okay, now to analyze scattering, though, we need to bring in the potential and actually solve the equation. In fact, what we're going to do is we're going to say, instead of phi 0, we're going to say phi KLM of R is going to be equal to some R KL of R YLM of theta and phi, and then we're going to write RKL of R as UKL of R over R. And at that point, then, the equation is Schrodinger's equation, minus h bar squared over twice the reduced mass, d2 dr squared plus L plus 1, h bar squared over 2 mu r squared, and then plus v of r, acting on UKL of r, is h bar squared k squared over 2 mu UKL of r, and then, as you know, you can further simplify things. There's an h bar squared over 2 mu almost everywhere, and so you can simplify things somewhat by, you see I don't have this here, but obviously what you would do is you just write this as minus d2 dr squared plus L plus 1 over r squared plus u of r. Well, unfortunately, we've got 2 u's. That was actually a lousy choice of notation. UKL of r is equal to k squared UKL. So that's the equation we actually are going to satisfy. And to get it to this, we have that u is equal to 2 mu over h bar squared g. So you multiply the top equation by 2 mu over h bar squared, all those factors go away, and you get a u here. So that's the equation that one actually analyzes. And as we saw last time, as r goes to, well, we also impose a boundary condition, namely UKL of 0 is equal to 0. This is the justification of this is that we're talking about positive energy solutions. We're not doing potential scattering. We're not doing bound states. But even had we been doing bound states, we would have had this condition for L greater than 0 for most potential potentials. At long distances, this equation becomes d2 dr squared plus k squared on UKL of R is 0. So that's the asymptotic behavior. And so U is a linear combination of, say, A e to the minus I kr plus B e to the I kr. And then one can argue that A and B have to be of the same magnitude, and the reason for that is that that this incoming wave, all of it goes out. We're talking about scattering without any absorption. And so this thing can be written as some constant times the sine of kr minus some beta sub L. And what is beta sub L? Well, it's whatever the thing is, so that when this thing, when we get near the origin, we get back to this boundary condition. And so, in other words, you solve this equation, you apply this boundary condition, and the asymptotic condition that A equals B, and then you wind up with something proportional to the sine of kr minus beta L at large distances. At small distances, you have something that's more like sine of kr. And then you rewrite beta L somewhat so that you write it as C sine kr minus L pi over 2 plus delta L. And this delta L is a big deal in potential scattering. The reason why you do that is you want to pull out this phase, because this is the phase that occurs in the spherical Bessel function at large distances. And so it is what occurs in other words, if there were no scattering, delta L would be 0, and you just have plane wave would come in and would just keep going and there would be no scattering at all if all delta L's were 0. Okay, then at large distances, this thing, in other words, EVI KZ at large distances just looks like this, and you have this as the base of L pi over 2. Okay, so that's basically a review, and this thing is called the phase shift. I guess the reason it's called that is that this is the phase of the plane wave. When you shift, you get a plane wave plus a scattered wave in a sum like this. Okay, well, if this is our U, what is our phi? Well, phi KLM of R, then, as R goes to infinity, is some C sine of KR minus L pi over 2 plus delta L over R YLM of beta and phi. And now we're going to write it the way we wrote, where is it? This one. We're going to write it like this, and we're going to say it's minus C YLM of beta and phi, and then e to the minus I kr e to the I L pi over 2 minus delta L minus e to the I kr e to the minus I L pi over 2 minus delta L, and this is all divided by 2I R. Okay, let me get rid of some of the erase some of this. Okay, so that's our expression, but what we want to do is we want to match this up to be a plane wave in the z direction plus a scattered wave, and so we multiply each of these partial waves. We multiply each of these partial waves by a phase factor, an overall phase factor. And so that means we call that phi tilde KLM of R, and it has the asymptotic behavior as R goes to infinity of minus YL M of theta and phi, and now e to the minus IKR e to the I L pi over 2 minus e to the IKR e to the minus IL pi over 2, and then e to the 2I delta L. In other words, we multiply each of these guys by e to the I delta L to get rid of this factor. And so we close this bracket, and then we divide by 2IKR. Okay, so whereas the plane wave looks like this, and at infinity looks like that, the partial wave looks like that. Over here, the partial wave looks like exactly the same thing, except the factor e to the 2I delta L. All right, so remember the way we've written our notation is that the full wave function is the incoming wave function plus e to the I k r over r f sub k of in principle theta and phi, although for spherical-symmetric potential there's no phi dependence. And we're going to write this as a sum, some sort of constants here, phi tilde KL 0, and it's 0 because there's no, we don't want any phi dependence in here, and in fact we don't need any for the e to the IKZ either. And so in fact, we're going to write this as a sum L equals 0 to infinity, I to the L, square root of 4 pi, 2L plus 1, phi tilde KL 0 of R. So in other words, it's the same expansion as over here, except that, and that is the same expansion as that, except that the I'm looking for the expression phi 0 here, that the phi 0 is replaced by phi tilde, which means that we've multiplied by the e to the I delta L, and we have a delta L in it because it has a scattered phase. All right, so
personally, I think that this is fine.
So what we do now is we just continue here, and this is a sum, I to the L. This is a sum, I to the L, square root of 4 pi, 2L plus 1. Well, I'm going to put a minus sign in front of it. YL0 of theta, and now that whole thing is being multiplied by 1 over 2IKR, and this structure here, which is e to the minus I k r. Frankly, one can write this as I to the L. I don't know why we don't do that. I guess I can call it minus I to the L. 2 pi I delta. No pi, wow. 2 pi delta L. Okay. Now what you can see is that this chunk here, together with all of that, just gives you the e to the I k z. And so this part is going to be the scattered wave. And well, it's a little more tricky than that. What we want to do is we want to take some of this and put it in there also. So let me just note this simple identity. E to the 2I delta L can be written as 1 plus 2I e to the I delta L sine delta L. And you can check that by saying, well, this is 1 plus e to the I delta L. Now, sine delta L times 2 pi I is e to the I delta L minus e to the minus I delta L. And so when you multiply through, this times that gives minus 1, which cancels this. This times this gives e to the 2I delta L. So that's the correct identity. So now we're going to substitute that in there. So when we substitute this in here, this thing becomes minus the sum L equals 0 to infinity I to the L square root of 4 pi 2L plus 1 YL 0 of theta, and then times e to the minus I kr e to the I pi L over 2 minus e to the I kr e to the minus I pi L over 2I kr. So that's what comes out from writing e to the 2I delta L as 1 plus this. The one term kicks out this. And then the other term leaves us with e to the I kr over r, 1 over k, e to the minus I L pi over 2, e to the I delta L sine delta L. Okay, so this first term here, this times that, is just e to the I k z. And the rest, by definition, is fk of theta e to the I k r over r. And so the scattering amplitude, fk of theta then, is this stuff, which is to say the minus signs cancel, there's a 1 over k, you pull off you factor out the EBI kr over r, and you have 1 over k, sum on L from 0 to infinity, square root of 4 pi 2L plus 1, e to the I delta L, sine delta L, and then a YL 0. Okay. So that's the final expression for the scattering amplitude for a spherically symmetric potential. Okay, now we can do two things. We can calculate, first of all, the absolute value squared of that is the differential scattering cross-section. And can integrate that over 4 pi steradians, we get the total cross-section. Another thing I should say is that not only have we been considering potential scattering for spiritometric potential, but we've always been assuming that there are no bound states, there's no absorption, there's no particle production, and consequently the momentum going out, the wave number going out, is the same as the wave number going in. That is to say, the kinetic energy of the particle going out is the same as the kinetic energy going in, and that's called elastic scattering. So this is the elastic scattering amplitude. All right. And as I said, the differential scattering cross section, d sigma d omega, is just fk of theta squared. All right, now what is the total cross-section? Well, the total cross-section is the integral of this over d omega, and so the total cross-section is the integral d omega and of this whole structure here. So that's 1 over k squared. And it's going to be a sum of L and L prime. The 4 pi's come in to square root of 2L plus 1, 2L prime plus 1, e to the I delta L minus I delta L prime, sine delta L sine delta L prime, and then y L 0 of cosine theta, y, well, of just theta. When you do y, you know, so that's a theta, and y L prime 0 of theta. Well, these guys are orthogonal and normalized on the unit sphere, so that just sets L equal to L prime. And so as a result, then, so the total cross-section is, after you do this integral, you have 4 pi over k squared, sum simply on L, 2L plus 1 from here. The phases cancel, and you get sine squared delta L. So that is the actual formula for the total cross-section in potential scattering. So you see, if these phase factors are 0, there's no scattering at all. Okay. So any questions? You can also see that the maximum value of any of these delta L's is of sine squared delta L is when delta L is pi over 2. And in that case, sine squared delta L is 1. And if they were all pi over 2, then what you have, it would be a completely divergent sum. It would be infinity squared, essentially. Now let's notice something that's kind of amusing. Let's multiply scattering. Let's look at the scattering amplitude. Let's look at the scattering amplitude in the forward direction and multiply it by 4 pi over k and see what we get. Well, first of all, I need to look at the imaginary plot of the forward scattering amplitude. So that's f, where theta is equal to 0. This then is 1 over k, sum, square root of 4 pi, 2L plus 1, sine, oh, the imaginary part. The imaginary part of E beyond, first of all, this guy is real. The imaginary part of E beyond delta L is simply sine delta L. So this is sine squared delta L. And YL0, as I said, it's real. It's that thing we wrote down earlier. In fact, what I should have done was, in other words, remember that this YL0 of theta is equal to square root of 2L plus 1 over 4 pi PL of cosine theta. And these Legendre polynomials are real. So when you take the imaginary part of this thing, the only part that is involved is the only complex part. So we get that, and then we get a square root of 2L plus 1 over 4 pi, and then PL for theta equal to 0. Well, that turns out to be 1. The Legendre polynomial P0 of theta is the number 1. P1 of theta is cosine theta. Cosine theta is 1 when theta equals 0. Now that doesn't prove it for all L, but it's true. And so what we get there for the sum is 1 over k, a sum, 2L plus 1, sine squared delta L. And so now you see that the total cross-section is equal to 4 pi over k times the imaginary part of the forward scattering amplitude. And this is called the optical theorem. Now, it's, as I said, it's called the optical theorem, and in fact, it's worth noticing and remembering. It's worth, in fact, even being, it's worth a lot of respect, this theorem. Because it's not simply true in potential scattering or spherically symmetric potentials. In fact, in quantum field theory, you can prove that the total cross-section, including everything, production, inelastic, elastic, everything, the total cross-section is the imaginary part, is 4 pi over k, the imaginary part of the forward elastic scattering amplitude. So what we just meant right here, elastic. So the generalization, and we were doing this in the context of non-relativistic quantum mechanics. When I say the context of quantum field theory, that's the context of relativistic quantum field theory. And there, the total cross-section, 4 pi over k, imaginary part of the forward elastic scattering amplitude. And so that's important. Notice something else, and I might come back to this next Monday. But remember that one has, remember the phrase dispersion relation. So if you imagine that this elastic scattering amplitude is an analytic function of k, say, then you can think about writing the dispersion relation for the elastic scattering amplitude. And remember, one of the things that happens is that you wind up expressing the scattering amplitude as an integral of its imaginary part. Well, that turns out to be the total cross-section. And so, basically, this optical theorem played a big role in dispersion relations. This was done a lot in the, I guess, the 50s, the 60s, and 50s and the 60s. And then it gave rise to a whole industry called analytic S-matrix theory, where S just stood for scattering. And people tried to say that, in fact, we could do away with on field theory, you just use things like dispersion relations. That led nowhere. That's. I'm exaggerating. It wasn't quite that bad. It did give rise ultimately to string theory, which again may also be leading nowhere. But by the way, before I erase this, it's worth looking at this. This, if I trust the blackboard, is cytosine, and it's not the whole of cytosine because the cytosine is linked to a sugar phosphate background, and the guanine is also linked to a sugar phosphate background. So there should be a sugar here somewhere, and then a phosphate group, and another phosphate group, and another sugar, and then another thing that's either guanine, cytosine, or adenine, or what is it, thymine? It's either uracil or what T stands for. Tyrosine? Okay. Anyway, I'm not sure you can names, as you guys know. What you have here is this is an oxygen, and this here is what you have here is a hydrogen, and the electron can come off the hydrogen and be attracted to the oxygen, and so it sort of sits in between. And when it sits in between, this is essentially negatively charged, this is positively charged, and they're attracted to each other. And there's also a hydrogen bond here, and this is called a hydrogen bond also. And you see there are three atoms that can participate in hydrogen bonds here, and three that can participate here. And so that also, notice here that guanine has 2 rings and cytosine has 1. And remember that this thing is then attached to a sugar and then 2 phosphates, and then again a sugar and another phosphate, and this goes up to the next one. So this is the sugar, this is DNA, this is the sugar phosphate, the 2 sugar phosphate backbones, and there's only a certain distance here, so you can accommodate 2 rings and 1 ring, but not 4 rings. You can't have 2 rings here and 2 rings there, because then things would be in each other's faces. Or if you had 1 ring here and 1 ring there, they'd be too far apart. And so what you have then is you have to have 2-1. In other words, if you have a 1 ringer here, you need a 2 ringer over there. And then it turns out that the only 1 ringer that will bond, that has the arrangement that matches guanine is cytosine. And so that's the basis of the genetic code, that you have A bonds with T and G bonds with C. And so that's how DNA works. Any questions before I erase it? What's remarkable is that in eukaryotic cells, at least in mammalian cells, the DNA, of course, has to be replicated every time the cell divides. And in the case of human beings, the DNA has something like 3,000 base pairs. Not 3,000, 3 billion base pairs. And when you're duplicating 3 billion base pairs, obviously you need to do it very precisely. Otherwise, you're going to have mutations. Kids are going to have 4 fingers and 3 eyes and an odd number of ears, and if they can survive at all. And So it turns out that the error rate is just remarkable that these molecular machines have an error rate that's, unfortunately, I don't remember what it is. I haven't looked at it lately, but it's down below 1.10 to the 6. It may even be 1 in 10 to the 9. But at any rate, it's do you remember what it is? Anybody remember? Actually, if you're online, you could Google DNA polymerase error rate of aliens. But all right, where are my notes? Oh, I guess I have them down. Anyway, it's just absolutely amazing that this error rate can be so low. All right, well, let's get back to the Born approximation just as an example of how you compute certain things here. And let me write the scattering amplitude then. So this is the first Born approximation to the scattering amplitude. And here, I'm going to use a slightly different notation. K is the incident beam, and K prime is the final beam. That is to say, goes in the direction of the observer at a distant point r. And this is equal to minus 2 mu over 4 pi h bar squared. Now with the integral dq x prime e to the I k minus k prime dot x, and why I was using x prime. Let's get rid of the primes. Okay, so remember it's the Fourier transform of the potential, and if you keep track of what the normalization factor is, that's what it actually is. And, well, we can choose, as usual, choose k minus k prime to be the z-axis for your polar coordinate system. And in that case, you can write this as minus mu over 2 pi h bar squared integral d phi integral d cosine theta from minus 1 to 1, 0 to pi, integral 0 to infinity r squared dr, e to the I, k minus k prime, cosine theta r, and let's assume that this is a spherically symmetric potential, so we have v of r there. And let me write Q as the absolute value of this thing is called the momentum transfer, K minus K prime. In other words, the original momentum is K, the final momentum is K prime, so the difference between the two is the momentum transfer. Okay, so the first thing is we do the d cosine integral. And, well, we do the phi integral, and then that's minus mu over h bar squared. And now doing the phi integral, that leaves us with the r integral. And this gives us e to the I q r minus e to the minus I q r. And we have then IQR in the denominator, and then V of R. And so altogether then this is minus 2 mu over h bar squared q integral 0 to infinity dr r V of R sine QR. Okay, so that's the expression. We can't continue because we don't know what V is, but that's the expression. And again, the scattering cross section, differential scattering cross section P6Z maybe is F of Q squared. This only depends upon Q, the absolute value of the momentum transfer. All right, now we can put in a particular potential. We can say, well, let G of R be equal to some V0 e to the minus mu R over mu R. Oh, nuts. You see now, I wanted to preserve this as the mu as the reduced mass, and now I introduce mu as this parameter here. So that's not going to work. What shall I call it instead of mu? M? Okay. Notice that this goes to 0 very fast as R is greater than 1 over m. So 1 over m is the range of the potential. So this integral then, this first Born approximation of Q is then minus 2 mu over h bar squared Q, integral 0 to infinity dr. There's a V0 and M. This R cancels that R, and we have e to the minus mr, and then e to the I cube R minus e to the minus I cube R over 2I, simply over 2I. Okay. All right, so let me tidy this up a little bit. This is, in other words, I mu V0 over h bar squared m q integral 0 to infinity dr e to the minus m minus I q r minus e to the minus mu plus I q r. In both cases, whoops, this is an M. It's a shame. My notes had it the opposite way around. Okay, these are easy integrals to do. The integral of this is very simple. So 1. So this first Born approximation then is I mu V0 over h bar squared m q m plus I q. Skip the line. 1 over mu minus I q over m. All right, I'm going to get this all screwed up because I changed one of my notes. Minus 1 over m plus I q. All right, that's right. And now we rationalize these fractions. And what we have is 1 of q is equal to I mu v0 over h bar squared mq. Let me skip along. 2iq over mu squared plus q as n squared plus q squared. Okay. Or altogether, it's equal to minus 2 mu v0 over m h bar squared m squared plus q squared. Now what is q squared? Well, q squared is k minus k prime squared, which is k squared plus k prime squared minus 2 k dot k prime But this is elastic scattering, so this is actually equal to 2k squared minus 2k dot k prime. And so this is equal to 2k squared times 1 minus cosine theta. So that's what q squared is. So d sigma d omega in the first form approximation with the Yukawa potential is the absolute value squared of this, and that gives us 2 mu v0 over h bar squared m squared 1 over m squared plus q squared squared. And that's equal to 2 mu v0 over h bar squared m squared 1 over m squared plus, and now q squared is, well, it's a trigonometric identity so that you can write it either the way I wrote it, which is 1 plus 2k squared times 1 minus cosine theta squared, or you can write it as 2 mu v0 over h bar squared m squared 1 over m squared plus 4k squared sine squared theta over 2. This is one of those half-angle formulas that are kind of mysterious. Okay, what does this look like at high energies? Well, at high energies, obviously it goes as 1 over k to the 4th at high energies, because all of this goes away. You can say, well, there's a b0 squared, there's a mu squared, there's an h bar to the 4th, and an m squared, but the important thing is that it goes down as k to the 4th. Now, also, you can see here that in the forward direction, the sine squared of theta over 2 is going to be 0, and theta is equal to 0. So in the forward direction, this k to the 4th behavior goes away. So in other words, although the cross-section in an arbitrary direction goes down at 1 over k to the 4th, in exactly the forward direction it doesn't go down. So there's a forward peak that's pronounced at high energies. And it's pronounced because the scattering is usually suppressed as 1 over k to the 4th in all other directions except the forward direction. On the other hand, at low momenta, low incident momenta, then the k squared term is essentially 0 and the scattering is isotropic and it's just S-wave scattering. In fact, that's something that we learned before, way back here. You can see that if k minus k prime is very small, then you don't expect to get much angular dependence. But the way, when we were analyzing our partial waves, what we said was, let's see, where was it? It was way, way back over here. JL goes as rho to the L, and consequently, it takes a while for the spherical, for the partial wave to build up, so so at very low energies, what you're going to get is the L equals 0 wave, because the L equals 0 wave is already big at the origin, but the L equals 1 wave goes up linearly. The two way it goes up quadratically. So, at low energies, you're going to have isotropic scattering. Okay, now we can take the limit, the other limit, namely the limit m going to 0, and let's see. I'm a little concerned though because of the factor m here. Oh, yeah. What we're going to do is we're going to take the limit. We're going to do something a little bit. I don't know even know what this is. Oh yeah. Let's look at what our potential was. Our potential looked like this. Okay. It had a V0 over an m. So we can take the limit. M goes to 0, but V0 over m goes to a constant value. And what happens in that limit? Well, in that limit, d sigma d omega goes to 2 mu v coulomb, we can call it, over h bar squared times 1 over 16 k to the 4th sine to the 4th theta over 2. Here, v coulomb is z prime e squared, and so d sigma d omega goes to 2 mu squared z prime e squared over h bar to the 4th, and then this factor 1 over 16 k to the 4th sine to the 4th theta over 2, and then the final version is, no, I don't see the point of writing that. It's exactly the same as, well, if we put it in terms of p, the h bar to the 4th and the k to the 4th becomes p to the 4th. So let me just use the eraser to indicate that. And this is a rough form. Okay. Another way of writing this, so let's write it one more time, is 1 over 16 z prime e squared over the kinetic energy of the incident particle squared 1 over sine to the 4th of theta over 2. And so once again, it's peaked in the forward direction. And the peaking this time occurs because this m, the blunt peaking at low energies, isn't there. So it's just always peaked in the forward direction. If you go to pi over 2, then you've got sine squared of pi over 4, which is sort of like 1 over root 2. If you go to pi, then you have maximum suppression because you have just this whole thing becomes 1 because pi over 2 is just 1. The sine of pi over 2 is 1. Okay, so this is the classical formula for Coulomb scattering. So you see, although we had some worries about the Coulomb potential, it basically worked out. Are there any questions? Remember, I do have chocolate. Okay. All right, so let's look at this again from a let's look at this first Born approximation again. So we've seen the first Born approximation as a function of q, the momentum transfer, is minus 2 mu over h bar squared q, integral 0 to infinity, dr r v of r sine qr. So that's the expression, and we can draw some conclusions, some properties from this. One, well, d sigma d omega is a function only of q, and q is that, and q squared is 2k squared times 1 minus cosine theta. So this is for a spherically symmetric potential. Spherically. Okay. 2, this potential is real, so F1 of Q star is equal to F1 of Q. So the scattering amplitude is real, and that tells us then that the first Born approximation doesn't have, although it tells us it's a reasonable approximation in many cases, especially when the coupling is weak. It tells us that it would tell us that the total cross section would be 0. In other words, you don't have enough information in the first Born approximation to compute the total cross section, even approximately, because the imaginary part of the forward scattering amplitude should be the total cross section. D sigma d omega is independent of the sign of V of R. So that means that whether you have an attractive potential or a repulsive potential, the first Born approximation gives you the same scattering cross section. And so you can imagine scattering an electron off a nucleus or an electron off another electron. You're going to get apart from the mass differences, you're going to get the same cross section to lowest order, which is somewhat puzzling. So you have to go to higher order. K prime, of course, is length of k times r hat, just the vector in the direction theta phi. And so q is small when k is small. So in other words, for low energies, obviously from this expression, q is small. And so for low energies, q is small, and so for low energies, F1 of q is approximately minus 2 mu over h bar squared q. And in fact, you can bring this q in here, and you can say sine qr over q should just be an integral 0 to infinity dr r squared v of r. Right. And equivalently, if you toss in a 4 pi, you can multiply that by 4, so then you have minus mu over 2 pi h bar squared. I'm sorry, I should have taken the q in there. Integral dq dex v of dq r v of r. In other words, it's the volume integral of the potential time, which is a constant, times minus mu over 2 pi h bar squared. So in other words, as at low energies, the first Born approximation becomes an S wave, and not only is it an S wave, but it's a constant independent of momentum, as the momentum gets small. So that was 4. And now number 5 is at the opposite direction. When Q is much, much greater than 1 over M, or 1 over the range of the potential. In other words, if you have Q going to infinity here, then what happens is this, you get that the sign of QR oscillates like crazy over the region. In other words, it looks like this. Suppose the potential looks like this. The range of the potential is this distance, say, R. And then you're multiplying V times QR. Well, as Q goes to infinity, the thing looks like that. And so F1 of Q goes to 0 as Q goes to infinity. I should have a better way of saying that, but I don't. Anyway, it's small as Q gets bigger than. Actually, it's not Q bigger than 1 over, it's Q greater than M. Because M is 1 over the range of the potential. Okay, now, I've been discussing all these in the case of spherical symmetry, but in fact, the last 3 properties are true for the first Born approximation, even in the absence of spherical symmetries. Spherical symmetry. So that it's independent of the sign of R is just because the differential cross-section is, in the first Born approximation, is the absolute value squared of Fourier transform of the potential, because it's the absolute value squared, it's obviously independent of the sign of V. Moreover, if it's the Fourier, again, it's a Fourier transform of the potential, as K and K prime go to 0, that Fourier transform is just basically a volume integral of the potential. And so it goes to a constant, whether or not the potential is isotropic. And finally, if the potential has finite range, and you set Q to infinity, you're taking the Fourier transform of something of finite range, and it just goes to 0 as Q goes to infinity. And so those occur whether or not it's isotropic. But the first 2 properties are consequences of it being a spherically symmetric potential. Okay. What else here? I guess there are a couple of more topics. One topic is this Lippmann-Schwinger formalism. Now, it's a. Do you want to see the Lippmann-Schwinger formalism? I guess we're sort of running out of time today. But let me just show you what it is. It's basically that you say that your scattering amplitude is a free ket corresponding to a plane wave plus 1 over E minus H0 plus or minus I epsilon times V times psi. That's basically the equation. And I don't know. It's a lot of mathematics. I'm not sure how much physics is in this. So what do you think? Do you want to? You guys want to see that next time? You think we should do things that are more physical?
More physics.
All right. Let's quit. I'll think about it. One thing that I would like to do is show you some connection between phase shift, scattering length, and bound state. See if we can get that done. See if we can work that in. All right. I guess we can this thing.
So click on